We're going to look at something called indefinite integrals. An indefinite integral is something that has an infinity in it in some sense or another. Well, what would it mean to integrate from 5 to infinity? Well, before I actually do the mechanics of this problem, follow me on this little thought process. What if instead of integrating from 5 to infinity, we went from 5 to 10? Well, just to see what would happen, I did that on the calculator and got a decimal. Then I went from 5 to 15, got a bigger decimal. Then I went from 5 to 40 and got a bigger decimal. There's nothing special about these upper limits, I'm just trying bigger and bigger numbers. But then when I integrated to 100, I got a bigger decimal, but not by much. And then I integrated to 600, and my decimal went up, but not by very much at all. And then I went up to 1,000,000, and my decimal didn't change all that much. I'm not suggesting that you would ever do any of these, but the notion of integrating to infinity is the sense of integrating to bigger and bigger numbers. And you can see here that when I do that, the answers get bigger and bigger, but it seems like they're approaching 0.6. So it seems logical that we would ascribe 0.6 as the value of this integral. Now, none of that is stuff you would ever do as a student. That's just an idea to understand what it means to integrate to infinity. Here's the actual definition. We're going to take this infinity and we're going to replace it with a letter, call it a. And we're going to look at the limit of the values of those integrals as a gets bigger and bigger and bigger, or as a approaches infinity. This is the formal definition of integrating to infinity. Now let's perform the mechanics. First, I have to calculate this integral, which works out to negative 3 over x. Pause here if you want to see the algebra that led to that. Then I can plug in a and 5 as my limits of integration. Remember, there's a subtraction involved when you do this, so that led to a double negative. Doing a little algebraic simplification leads me to this limit. Well, what is happening to this expression as a approaches infinity? Let's do the limit. This term on the right is becoming 3 over bigger and bigger and bigger numbers, and hence is approaching or tending to 0. So this limit is therefore 3/5 minus 0, and of course that's 3/5, and that's the answer to this problem. We're now going to look at an application of the indefinite integral. We're going to find the area of an unbounded region between this graph and the x-axis to the right of negative 4. To understand what that means, we want to find the area under this curve from negative 4 forever rightward. Now, just to give you a sense of what this might mean, we could compute the area from negative 4 to 6. That would seem to cover most of the area we're trying to calculate. Or we could calculate it out to 10 or even 15. But of course, we want to find the area for all x values greater than negative 4. So what we really want to do is integrate out to infinity. And in some sense, what we're doing here is we're calculating an amount of area that may be finite while still in an unbounded region. This region goes on forever, but strangely, as we'll see, it does not have an infinite amount of area. So what we're going to do here is calculate the limit as m approaches infinity, replacing the upper limit of integration from infinity to m. This should give us, if it is finite, which it turns out to be, the amount of area under that curve in that infinite amount of space. So first we have to compute this integral itself, which turns out to be this. Hit pause if you'd like to analyze the algebra. Then we have to plug in m and negative 4 and subtract, as we always do for integration and substituting the limits. From there, I did some algebraic simplification. I'll go a few steps down here. and hit pause if you want to take a moment to analyze all the messy particulars. But now, as m approaches infinity, this term here turns out to approach 0. And here's the reason. Think of a negative exponent as a reciprocal. And what's happening to this expression on the far right as m approaches infinity is the denominator is getting bigger and bigger and bigger, and hence 5 over something that's getting bigger and bigger and bigger is approaching 0. The first term isn't changing as m approaches infinity, which ultimately leads us to this answer. There's nothing wrong whatsoever with this answer. I personally don't like decimals as much as I like fractions, so I changed the 0.8 into 4/5. A student wouldn't have to do that necessarily. And let's analyze what it is that we just calculated. Well, we calculated this integral, and we got an answer. But remember, we're looking for a finite amount of area in an infinite amount of space. And so we've just calculated and shown that while this pink area here goes on forever to the right, there's only a finite amount of area, specifically 5 times e to the 4/5 square units, under that curve.